Feel free to go from slide to slide to view how to do each type of problem with the recorded answer key. In order to decide if the ordered pair 5, 2 is a solution to the system, you just have to plug it into each equation. So remember, the x-coordinate goes in the place of x and it comes first. And it has to be a solution to both equations, not just one. So it does work for the first one. All that means so far is that 5, 2 is a solution to this equation or a point on that line. Then we also have to check it for the next one. So 2 times 5 plus 8 times 2. And obviously that's not going to come out because it's 10 plus 16, which is not 11. So no. So the answer that you write is no, it's not a solution to the system. And all of this right here would be your work to support that answer. Remember, you can't just say yes or no without work to support it. So to solve by graphing, we're first going to graph each line separately. So I'm going to graph that first line in red. And you have the choice of whether or not you want to make a table, use x and y intercepts, or slope-intercept form. Many people use slope-intercept form, but keep in mind both of these actually seem to will be quicker to use x and y intercepts. So remember, to find the y-intercept, I change x to 0, so y would be 6. And to find the x-intercept, I change y to 0, so my x-intercept would be negative 3. And I can add some more points since the rise is 6 and the run is 3. You can kind of think of that as 2 over 1. So that means every point is 2 over 1 away. So over 1 up 2, over 1 up 2, and you can see that it actually lands kind of on there. And I'm putting multiple points. 1, because I don't like graphing lines and explain everything, but 2, because hopefully when I graph the blue line, one of these points will exactly land on that line. Although I should put a line, so I will. Move that over. It's not perfect, but it's okay. And so this line I'm going to do in blue. So if I change y to 0, my x-intercept would be negative 1. And if I change x to 0, my y-intercept would be negative 2. Because negative 6 divided by 3 is negative 2. So this has a rise of 2 and a run of 1, but it's negative. So I can do multiple points. So I could keep going this direction, but it's obvious it's going to intersect somewhere over here. So go up 2 over 1. Hey, look at that. It intersects. I'm just going to do a couple more. And then I'm going to put that line. Again, not perfect. So keep in mind, a lot of people stop there. You actually haven't done the solving yet. All you've done so far is you've successfully graphed lines. But to actually solve, you need to say the solution, which would be negative 2, 2. And you could also check that by replacing x and y with negative 2 and 2 in both equations, and it should work. So to be able to solve by substitution, the first thing that needs to happen is one of your variables needs to be isolated, which it is. My y is isolated in that first equation. Actually, my x is isolated also, but that's okay. So this equation says everywhere you see a y, you can put an x minus 2 in its place. And I do see y. So in that second equation, I'm going to rewrite it. But instead of writing the variable y, I'm going to write x minus 2. And now I'm going to solve it like a normal one-variable equation. And before I do that, I'm going to make those plus negative. So I get x equals 17 plus, and then I'm going to distribute negative 4x plus positive 8. Be careful with that. That comes from the fact that it's a negative 4 and a negative 2. Then I can add 4x to both sides. So I get 5x equals, and I can actually combine 17 and 8 to get 25. Divide both sides by 5, x equals 5. I'm not done yet because the solution to a system is an ordered pair. So I still need to find y, and this says that y equals x minus 2. So I can take the x that I just got, which was 5, and say that y equals 5 minus 2, which would be 3. And so then to express your final answer, you express it as an ordered pair, 5, 3. So I'm still solving by substitution. The directions didn't change. So to do that, I need to isolate one of my variables. So I'm going to isolate x from the first equation. So I'm going to change I'm going to isolate y. So I'm going to change it to say y equals negative 3 minus x, because to do that you minus x from both sides. So this says everywhere you see a y in that first equation, you can replace it with negative 3 minus x. So 5x plus 2 times, instead of y, I'm going to say negative 3 minus x equals 9. If I distribute, I get negative 6 plus negative 2x equals 9. If I combine like terms, I get 3x, and then I'm also going to add that 6 to both sides in one step. X equals 5, and then I still need to I can take this x equals 5 and I can plug it actually right back in there. So negative 3 minus 5 would be negative 8 for y. So 5, negative 8. And that's my final answer. So in this example, it's a little strange because y is isolated in both places, but this top equation would just say, if you see a y in the second equation, replace it with x minus 4. And you do. So the y that's before the equal sign becomes the x minus 4, and then 18 plus 2x minus x. Negative 4 equals 18 plus x minus 18 from both sides. You get x equals negative 22. And then if I take the negative 22 and plug it in there, you get y equals negative 22 minus 4, which is negative 26. So final answer, negative 22, negative 26. So the first thing I'm going to do in this problem involving popcorn and pretzels is identify what I want x to stand for and what I want y to stand for. So x is going to be popcorn, and y is going to be number of pretzels. And the easier equation to write is the one that involves the money. So we know that popcorn is $2.50 a bag, pretzels are $2 each, and they made a total of $336. So that's my first equation. The second equation comes from the fact, and you can kind of check things off as you go, so I used all that information. The thing I didn't use is that they sell twice as many bags of popcorn. So here's my popcorn, that's x, as pretzels, and they sell more popcorn. So since there's more weight on this side of the scale would tip that way, and it's twice as many, so I'm going to multiply by 2. I'm going to put more weight on that side to even it out. So my second equation is x equals 2y. So this says everywhere you see an x, replace it with 2y. I do see an x, so I'm going to do 2.5 times 2y plus 2y equals 336. And then 2.5 times 2y would be 5y plus 2y equals 336. If I add those up, it adds to 7y equals 336. Divide both sides by 7, and I get 48. So 48 pretzels. And if there are 48 pretzels, 2 times 48 would be 96 bags of popcorn. So when you're eliminating, you're going to either add or subtract to get rid of one of your variable terms. So negative 3y and 3y can cancel out by adding. So I'm going to add those two equations together. And I'm going to add all the like terms that I see as I go. So I'm going to show that I'm adding. So 4x plus negative 2x is 2x. Negative 3y, and it's negative because of that, so negative 3y plus 3y is 0. That's why it cancels. And then 5 plus negative 7 is negative 2. Divide both sides by 2, x equals negative 1. So then if I plug that in here, negative 2 times negative 1 would be 2 plus 3y equals negative 7. Minus 2, I get 3y equals negative 9. Y equals negative 3. Final answer of negative 1, negative 3. On this example, I'm going to subtract because negative 4 minus negative 4, negative 4 minus negative 4 become plus positive and cancel. So that's kind of why I'm subtracting. So 6x minus 3x is 3x. Negative 4y minus negative 4y cancels. 14 minus 1 is 13. Not the greatest answer.
But x equals 13 thirds. You could change it to a mixed number, which would be 4 1/3. But when you replace x in either of these equations in 1 second, we're going to do it as an improper fraction, so it just makes sense to leave it as the improper fraction. So now to do that next part, we're going to do, let's say 3, we'll do the second equation. So 3 times 13 thirds, which will actually be nice because the thirds will cancel. 13 thirds minus 4y equals 1. So my 3's cancel. 13 minus 4y equals 1. If you subtract 13 from both sides, you get negative 4y equals negative 12, and y equals 3, for a final answer of 13 thirds comma 3. So while x wasn't great, y wasn't bad. So that's your solution. So on this example, if our objective is to eliminate, I'm going to keep the top equation the way that it is. It's in standard form. But I need to rewrite the second equation so that way it's stacked, kind of variables on top of variables, equal sign on top of equal sign. So to do that, I would subtract 3x from both sides, making it negative 3x plus 2y equals 6. So I took the second equation here and I rewrote it so that way it was in standard form by subtracting 3x from both sides. And instead of saying 2y minus 3x, I also changed the order so that way it's negative 3x plus 2y. And so now because my x's match their absolute value, you can add 3 and negative 3, and that's going to eliminate the way that I want. So 3 plus negative 3 is 0, 4y plus 2y would be 6y, and negative 6 plus 6 is 0. And a lot of people stop. They might find that confusing, but y isn't isolated. So we're going to keep going and divide by 6, so the y coordinate is 0, which is fine. 0 is a number. So now to find the x, I'm actually going to plug that into this second equation right here. So I would get 2 times 0 is 0 equals 3x plus 6. I would subtract 6 from both sides to isolate x, and then divide by 3, and x equals negative 2. So my final answer is negative 2, comma 0. That would be the point of intersection. So here, just make sure when you add negative 6 and 6, it's actually 0. 0 is fine. So as long as you're bringing down that equal sign and you always have something on each side, you should be fine. So for these two systems, we're still trying to solve by elimination. The difference is if you look at, say, the first example, if you add x plus 2x would be 3x, and x minus 2x would be negative 1x, so they wouldn't cancel. Same thing with your y's. You'd either get 8y or negative 6y. So because of that, we have to multiply an equation, and this goes back to chapter 5 with standard form. As long as you multiply every single thing all the way through by the same number, it's an equivalent equation, you're allowed to do it. So I'm going to multiply the top equation by 2. And what that's going to get me is 2x plus 2y equals 4. And don't forget to also multiply this number by whatever you're multiplying by. A lot of people forget that. The second equation that I had, 2x plus 7y equals 9, I don't have to change that one because they already have matching coefficient. It's kind of like when you add or subtract fractions, you need a common denominator. Sometimes you have to change one fraction, the denominator, and sometimes you have to change both. Here I only had to change the top equation, the bottom equation was fine. So now I can subtract, because 2x minus 2x cancels. 2y minus 7y would give me negative 5y, and 4 minus 9 would give me negative 5. So divide both sides and you get y equals 1. I'm going to go back up to this original equation with the smallest numbers, and I'm going to replace it. So x plus 1 equals 2, subtract 1, x equals 1. So final answer of 1, 1. On this example over here, you're looking for what's the smallest number you could either make the x's or the y's to match. So I can make the x's into 20s by multiplying by 5 and by 4, or I can make the y's into 6s by multiplying by 2 and 3. And since those are slightly smaller numbers, that's the one that I'm going to do. So I'm going to multiply the top equation by 2 to get 8x minus 6y equals 16. Remember, every single piece needs to get multiplied. And the bottom equation I'm going to multiply by 3, and I'm going to get 15x minus 6y equals negative 33. And because it's negative 6 and negative 6, that means I need to subtract, because negative 6 minus negative 6 will become plus positive, which would cancel. So I'm going to subtract. So 8x minus 15x would be negative 7x. And then 16 minus negative 33 would be positive 49. So an x equals negative 7. I'm going to plug that into my very first untouched equation, this one right here. So 4 times negative 7 would be negative 28 minus 3y equals 8. If I add 28 to both sides, I'd get negative 3y equals 36. And if divided by negative 3, I'd get y equals negative 12. So final answer of negative 7, negative 12. Don't forget that while you're doing all of these problems, you should be taking your final answer and I'm plugging it into both equations to make sure it works. That's the only surefire way to make sure that your ordered pair is the point of intersection. Because if it works for both, then you can be confident that you have the right answer. If not, you want to go back and try to find where your mistake was. So for this example, I'm still going to solve by graphing just because it tells me to, but the fact that it's a special type and the directions say that it has one, none, or infinite, I might expect something funky to happen. So I'm actually going to graph this bottom equation first in red because it's already in slope-intercept form. So it has a y-intercept of 1 and a slope of -3/2. And I'll do that in both directions. And then my second equation, if I put it in slope-intercept form, if I subtract 3x and then divide by 2, I get y equals 5 minus 3/2x. So even though I can see that they have the same slope, -3/2 and -3/2, it specifically asked me to solve by graphing. So I'm not done until I actually do that. So I start at 5 and then down 3/2, down 3/2, and the fact that they're coming out to parallel lines is a good thing because I saw they had the same slope, so that should be my expectation. And that would mean that this system has no solution, since the solution is the point of intersection and these two lines will never intersect. So again, on these examples, I'm just going to solve by the method indicated. So this says solve by substitution, and y is already isolated. So I'm going to make the top equation into x minus 2 times 1/2 x plus 2. I just substituted that in. So then I have x minus 2 times 1/2 x would be x, and then don't forget this is really -2 being distributed, so plus -4. If I do it like that. And then my x's cancel. -4 equals -4. And so for that I say infinite solutions. Keep in mind that each equation in the system, this is a line and this is a line. And you're telling basically how many times they intersect. So these two lines would intersect infinite times. We don't say all real numbers because you can't choose any ordered pair on the coordinate plane. All the ordered pairs that exist, if you think of all the ordered pairs up, down on the y-axis, left, right on the x-axis, they don't all land on these lines. But these two lines have infinite points in common, so infinite solutions. And then this, I'm going to solve by elimination, and I'm going to subtract because 2x minus 2x is 0. But then -3y minus -3y is also 0. So I'm left with 0 on the left-hand side. And then 6 minus -4 is 10. 0 doesn't equal 10, so that system has no solution. So on these examples, it specifically tells me to not solve it without actually solving it. So that means I can't graph, I can't substitute, I can't eliminate. And even though on this example, elimination obviously would be really easy, you can just add them, I'm not going to do that. And on this example, you could substitute because y is isolated, I'm not going to do that. So the way you make this determination is you kind of have to figure out, well, are they parallel lines, are they the same line, or are they neither? And to do that, we need to know the slope and the y-intercept of each line. And the way that you are able to identify the slope and the y-intercept of any line is you put it in slope-intercept form. So this top black equation right here, I would minus 5x, so 3y equals 6 minus 5x, and then I would divide by 3. So y equals 2 minus 5/3 x. So my y-intercept is 2, and my slope is -5/3. My second equation, I would add 5x, so -3y equals 3 plus 5x, and then divide by -3. So I get y equals -1, that's my y-intercept, minus 5/3 x, and that's because it's a positive 5, -3. So a slope of -5/3. So since my slopes are the same, but my y-intercepts are different, then they're parallel lines, which means this system would have no solution. So I didn't actually solve the system. I didn't graph, substitute, or eliminate. I just compared the slopes and the y-intercepts to make the determination. So on this one over here, the red line is already in slope-intercept form, and you can see the slope is 2, the y-intercept is -4. And for the blue line, you would add 6x. So 3y equals negative 12 plus 6x, and then divide by 3. So y equals negative 4 plus 2x, and so you can see the slope is 2. The y-intercept is negative 4. Both items are exactly the same, which means they're the exact same line, which means there's infinite solutions. So just like with a system of equations, the ordered pair has to be a solution to both equations. Same thing with inequalities, it has to be a solution to both inequalities. And just a review from chapter 6, a solution to an inequality is always in the shaded region, and it's only on the line if the line is solid, like these lines. If it's a dotted line, that just means the line is the border, and the points on that line actually aren't part of a solution. So what they're showing you here is the overlapping shaded region. So this line right here actually would have been shaded all the way along it. Let's say that was like red. And then this line right here, the negative slope, would have been shaded all the way along here, and let's say that was blue. This would be the purple overlapping shaded region. So to check if 2, 1 is a solution, I'm going to plot that point, so over 2, up 1. And since it's in the overlapping shaded region, that's pretty easy, it's a yes. For negative 2, 0 on the next one, I'm going to plot that point, which is right here. So now, let me just say this is like the red line, and then maybe this is the blue line. So the point negative 2, 0 would be a yes for the red line because it would be in the shaded region of the red line, but it would be a no for the blue line because the blue line is dotted, and dotted lines don't count as part of the solution set. So this one is no, this first one would be yes because it's a yes to both, and the second one would be no because it's a yes to one but not the other. So to graph a system of inequalities, the first thing we're going to do is graph each inequality as its own separate inequality. So remember, when you graph, you actually treat it as an equation. So I'm first going to graph x minus 4y equals negative 8, and to do that I'm going to use x and y intercepts. You could use slope-intercept form, but the intercepts are pretty easy. The x-intercept is negative 8, and the y-intercept is positive 2. And when you connect these, since the inequality is less than or equal to, I'm going to connect with a solid line. So I'm actually going to go back and grab a line here. And it's not perfect. There we go. And then I'm going to test the origin since the line doesn't pass through it, and I always test in the original. And the origin says, if you plug it in, the inequality says that 0 is less than or equal to negative 8, which it's not. 0 is greater. So that means I'm going to shade not with the origin, but this side. So that would get shaded over here. So if this were one inequality and not a system, the solutions would be all along the blue line and then also in the shaded region. But now I'm going to also shade, I'm going to draw the red line, which I'm going to think of as just regular x equals 8. X equals 8. And so that's the line where the x-coordinate is always 8. So here's an x-coordinate of 8. And then that would be 8, 0. This would be 8, 1, 8, negative 1. And this time when I connect, because the inequality is less than, I'm going to connect with a dotted line. And if it's time to when it's time to shade, I'm shading the space that's less than negative 8. And I have a vertical line, so I can either shade to the right or to the left. If you think of a number line, to the right would be greater, to the left would be less. So that's where I'm going to shade. I'm going to shade the red line as if the blue line didn't exist. I'm going to shade the entire red line. So all the way up and down. Just to show that they each have their own set of solutions. But now the solution to the system would be in this overlapping shaded region, and then also along this portion of the blue line that falls within the red shaded region. So any of those points would be ordered pairs. The graph by itself is the solution. You don't have to say anything else. So the first line I'm going to graph here is x equals 0. So obviously the origin, x equals 0, but then x equals 0 all up and down here as well. And if I go back to the original inequality, it has that or equal to,
So that also means that it's going to be a solid line. And since I'm shading the space greater, I would shade to the right. But I'm just going to put a little marker showing, okay, shade only to the right of the left line. You can't shade on this side, so it's just a little reminder. Y is greater than or equal to 0. I would graph as y equals 0, which here y equals 0, here y equals 0, here y equals 0. And it's going to be a horizontal solid line. And since it's greater, I would shade above. Now since I can only shade to the right of the red line and above the blue line, right now my overlap is in quadrant 1. And then I'm also going to do this line, and I'm going to put it in slope-intercept form. So negative y equals 10 minus 6x, which would make it positive, negative, positive. So my y-intercept would be negative 10, and my slope would be positive 6. So 1, 2. Go up 6 over 1. And this time when I connect, I'm going to connect, oops, something's off there. This time when I connect, I'm going to connect with a dotted line. It's not perfect, but this is because it's just less than. And if I plug in the origin, I'm always going to plug in the original. Notice that when I put it in slope-intercept form, I didn't even use an inequality because it didn't matter. So back to the original, 0 is less than 10. So that means shade with the origin, so that's on this side. But I can't go below blue, and I can't go to the left of red. So if it's got to be on this side of the black, it's going to be in this shaded, this overlap right here. That's my solution. Now to write a system, let me call this, make that blue, make this one red just to differentiate. So the red one, it's a horizontal line, so I know that it's, if it was an equation, it would be y equals a number, which would be 2. Since it's dotted, it's either less than or greater than. And that one's pretty easy, it's shaded above, so it's got to be greater than. The blue line has a y-intercept of 4, and it has a slope of down 2 over 2, negative 1. And the origin, here's the origin, you can see that the blue line got shaded with the origin, so I want it to be true. And so that would say 0 compares to 4. I want it to be true, so 0 is less than 4, and it's solid, so maybe less than or equal to. So that's my system. This one over here has 3 lines. It has this bolded line right here, this bolded line right here, and then obviously the slanted line right here. So the bolded line, the bolded blue line is y is always 0. It's shaded above, so it's greater than, and it's solid, so y is greater than, which is 0. The red line is x is always 0. It is solid, and it's shaded to the right, so greater than, which is 0. And the black line has a y-intercept of 2 and a slope of 1. And it's shaded with the origin, so that would be 0 compares to 2, so that way it's true, less than, and it's solid, so or equal to. That's that system. Here's just a review of places you can find extra practice. It tells you what the topic is and where in the book to find it. If it comes specifically from the practice part, like each section, make sure you can check odds in the back of the book for answers.